Masoud Akbarzadeh. Masoud is an assistant professor of architecture and structural design in the Weitzman School of Design. He directs the Polyhedral Structures Lab. Masoud combines his training in civil engineering, computation, and design to create really cool and exciting three-dimensional structures. So these are the types of structures that one sees in futuristic sci-fi movies, and the one that, you know, some of us dreamed about building. Oops. Somehow something happened. Okay, sorry about that. For some reason, I got kicked off of Zoom just now. I'm assuming everyone was still here. So let me just finish my intro and we'll get started right away. So I was just going to say that, you know, looking at some of Masoud's portfolio, that some of the structures that he works on and he designs are some of these things that, you know, as a young engineering student, I used to dream about. That I thought I would be able to, you know, that one would be able to do if, you know, one took, after one took your first engineering statics course. And of course, I was very, you know, thoroughly disappointed. Nevertheless, so this is some of the really cool stuff that Masoud works on. He's a recipient of the SOM Foundation Award, as well as an NSF Career Award. And today he's here to tell us about his current work and interests. So without further ado, please help me welcome Masoud Akbarzadeh. Please go ahead.
Thank you very much. Thank you very much, Larry. And do you hear me now? Everyone hears my voice?
Yes.
Excellent. By the way, that was the most exciting introduction I've ever heard for my work. I really appreciate that. Thank you. Hello, everyone. My name is Masoud Akbarzadeh, and I'm also, as mentioned before, I'm the director of Polyhedral Structures Lab and an assistant professor of architecture and structures at the Weitzman School of Design. I'm going to talk about spatial efficiency in my lecture. And basically, I would give you a brief introduction to the mission statement of my lab. I would introduce the graphical form finding methods that is quite intuitive, but very exciting. And then give you an introduction to my main research area, which is three-dimensional version of that graphical form finding. And then show you some design methodology that we develop in the lab together with educational and computational packages and tools, and including some theoretical research that involves both mathematical side of the work and material and construction exploration. And finally, I conclude with the nature and natural structures. So disclaimer, there's not going to be too much about robotics. So that's what I'm actually hoping to basically develop a kind of common ground that we can work together with the faculty at GRASP to develop that aspect of the work. So I established Polyhedral Structures Lab in January 2007, and currently I have 3 PhD students and 1 postdoc from ETH Zurich, 2 other postdocs that I had last year. One of them became an assistant professor at City College in New York, and the other at University of Montreal, but they're becoming involved in the research, and they stay involved even today with the project they initiated with me. So to just give you an overview about the approach of the lab, what we do and what is our approach. As I said, I am working in the lab together with my team, obviously, on the 3-dimensional graphical statics for education, design, and optimization of architectural structures. So we conduct theoretical research, which includes design methods, and then we apply those theoretical methods in the construction research, which is related to material methods. So these 2 directions primarily establish the research domain of the lab. And I would say the primary domain of the activities are within the field of architectural design and structural engineering. But recently we were able to expand this domain to mechanical engineering, material science, computer science, mathematics, and hopefully soon in natural sciences too. So before I talk about my research, I'm going to start with an important concept, simple but super important concept that introduces the efficiency in the geometry of the structure that we are dealing with. I don't know whether you're very aware of this or you've been acquainted with this concept, but Robert Hooke in 1676 introduced a really, really interesting concept as if you hang a piece of chain, based on its own self-weight, it would create a form that is called a funicular form or a catenary form, that this form is in pure tension. More importantly, if you reverse that form, it would be in pure compression. Means that if you take a section at any point along the geometry of this form, either in tension or compression, the only internal force that you get in the section of the form is basically a tensile or compressive force. In fact, we don't have any bending moment, and always the direction of the internal force is perpendicular to the cross section, which makes the system quite efficient. So in fact, material aligns itself with the direction of internal force. So you don't have any redundancy of the construction. If you know this concept, probably you know that Gaudi has used or embraced this concept really well in his work. In fact, Gaudi was more than a designer. He was a magician, I can call, who could elegantly combine engineering principles with architectural design. And he was taking this simple concept and building structural models for his buildings prior to any architectural design. So he was coming up with the structural form, and then on top of the structural form, he was adding the architectural detail to it. That's probably the reason that his buildings are becoming one of the exemplary in the field that does not have any time and it doesn't age. So through the history of building construction, if you look at, there are many examples that in all these examples, in fact, the designers tried to use these funicular forms and basically utilize these funicular forms in developing spaces that clearly shows the efficiency in the flow of forces or the use of material together with the elegance, which is the inherent property of using such elegant forms. So the problem of finding funicular form has become a point of interest among practitioners, researchers, designers, and engineers in the field of structural design and architecture. Right? Primarily speaking, there are three directions or the methods that you can find these funicular forms or efficient structural forms. One is the method that proposed by Hooke, and Gaudi used it a lot, which is physical form finding technique. The other one is numerical method that superseded the physical. And the last category is actually graphical. I'm going to mainly talk about graphical because it is based on geometry. Geometry is the common language between engineers and architects. It's intuitive. Everything is explicit and you can see everything. You don't have to calculate everything, which is more preferable for architects and designers. But in the meantime, I'll show how powerful this tool is and what you can do with that. So probably one of the most prominent examples of graphical analysis and basically instances that mathematicians became interested in geometry-based equilibrium principles are the works of French mathematician Varignon. So he was interested to investigate the geometry of funicular forms that are pure tension or compression and find geometric techniques to find the magnitude of the force and describe these forms or their equilibriums. So simply put, if you start with a piece of rope that has been pulled from three sides, it's just enough that you put a line perpendicular to each of the rope. These lines together would create a closed polygon. This closed polygon basically tells you that the system is in equilibrium. And if you measure each length of this polygon, which tells you how much force goes into each piece of rope. You probably had this concept in high school as a free body diagram or closed polygon of forces. That's exactly the same thing. So simple enough, if you have a funicular form that you have basically the direction of the applied loads and the geometry, you know that each node, the equilibrium of each node can be represented by the closed polygon. And thus, these polygons together would create a force distribution or the geometry of the force distribution that explains the equilibrium and more importantly, describes the geometry, because each edge of your geometry is perpendicular to each edge of this polygon. This principle, simple enough, became the basis of the method that was called later graphic statics, or originally graphical static by Coleman at ETH Zurich in 1866. So that was the first person who actually put this together in the form of a book and start to teach that to engineering architecture students. So what is graphical statics? Basically, graphical statics is a tool that in which you have a funicular form, that you can basically find a funicular form that is shown on the left. And you have another diagram, which is again geometric diagram. That is the force diagram, and that represents the equilibrium of forces within that funicular form. So everything is explicit. How? We know that per node in your funicular form, you should have a closed polygon. And basically, if you measure the length of that closed polygon, that tells you how much force will go into that. More importantly, because these two diagrams are topologically reciprocal and geometrically perpendicular, you can play with the geometry of one and then see the effect of that play in the other geometry. You can basically control your funicular height and see the magnitude of the forces are basically changing accordingly, right? Again, because everything is described using geometry, you can optimize geometrically really, really fast. For instance, in this method, the force diagram is constrained to a circle. As a result, the edge length equals to the radii of the circle, right? So that means that the bottom chord of your structure would have a constant force in it. So immediately you can see why the optimization is happening and how you can control, right? So what does that mean in terms of construction efficiency? Well, I'll take you to the City Hall subway station in New York City. This was built in 1913 by Guastavino, and it's called Guastavino vaulting. If you didn't know, the entire weight of this City Hall is actually sits on top of this vault system that only consists of 4 layers, 4 centimeters of 2-layer clay tile bricks with no reinforcement. So you can imagine that it's been living right now for almost 100 years, even more than that. And without any reinforcement, it works really well. So why this works? Because Guastavino, as you see in the image, he was using graphical methods to find that efficient form, which is that arch, and he built that efficient form using 2 layers of clay walls, which only less than an inch, the thickness of each layer. And then he's showing the load testing of that immediately in front of you. This is one of his built arches, and it can take up to 500 times of its own weight. That clearly shows that without any reinforcement, you can still design efficient systems, right? Even Gaudi, who is famous for his physical form finding technique, used a lot graphic statics to describe the geometries. This is a park wheel. If you haven't been there, you should definitely go visit this place. This is fantastic. Many people around the same time who had to work with the construction material, which was a stone and masonry at the time, they had to become masters in using graphical methods because the force flow that keeps the entire masonry structure in compression was necessary. This is another image of a cathedral designed by Zorn, and you can see the diagrams of forces on the corners and basically the funicular form of the arch. All right, if you didn't know, even the Eiffel Tower has been designed using graphical methods. Again, there are many examples of the use of the graphical methods in the design and construction of building bridges and really efficient arch structures. But the main limitation up until 2016 was that for the past 150 years, it has stayed as a 2-dimensional method. So when I started my PhD in 2016 at ETH Zurich together with the block research group, the question was quite clear. What is the 3-dimensional version of that method? And at some point through the history, basically was substituted by the numerical methods because of the calculation speed, and no one had a patience to basically draw the geometric diagrams. But again, today with the tools that we have, with the computational tools and representational medium, it's much easier to explore and to explore the potential of using this method. Anyways, if in 2D we have a single node that the equilibrium of the single node can be represented by a closed polygon of force, simple enough that you can measure the edge length and this basically measure the magnitude of the force in the system. What is the three-dimensional equilibrium of that? So I remember that I searched the history, the literature, and I realized that William John Macquarie Rankin, who was a mechanical engineer, by the way, in 1864 published a publication which is only a half a page. This is the entire publication. Right? This is from the start to the beginning. As you see, it's just 3 paragraphs in Philosophical Magazine. No illustration, no proof, nothing. And he calls it Principle of the Equilibrium of Polyhedral Frames. And the first sentence is actually a referral to his own book. And he's mentioning that, okay, this is the three-dimensional of what I already proved in 2D. But the theorem starts in the main paragraph, and it's only a 1-sentence paragraph. Probably that was the reason that no one actually looked at this paragraph, because it was really hard to understand it. I'm not going to read it for you. If you had a chance to search it online, try to read it and see what you can actually imagine from that. But anyways, the gist of the story is that if in 2D, the representative of a node, the equilibrium of a node can be represented by a closed polygon, in 3D, a closed polyhedron of force can represent a node, a spatial node in equilibrium, where each member of that node is perpendicular to a face in that force polyhedron. If in 2D, the length was representing the magnitude of the force, here the area can represent the magnitude of the force. If you're interested in proving that, use a Stokes theorem. Anyways, I was able to take the 2D graphical statics that was existed for 150 years, I would say, to the three-dimensional version of graphical statics that are based on reciprocal polyhedral diagrams. The immediate outcome of this is that if there is a single polyhedron that is convex, that is closed, this can represent a node in equilibrium in space. That also means that if you have a single polyhedron, you can start adding more polyhedrons of forces to that, but together they can actually describe the force distribution of a spatial funicular form that was previously probably really difficult to find that, only through certain form finding techniques. And if you had gravity and not gravity, it was really difficult. But anyways, with this method, you can immediately construct that and control its topology. Why? Because every node within your network can be described by a closed polyhedron, meaning that the equilibrium of that node, right? And the magnitude of the force in each member or each thrust is basically represented by the area of the corresponding face in the force diagram. With a little bit of patience, you're able to basically assemble a force diagrams that from which you can derive non-conventional spatial structural forms. So this is the key. We do not start from the form diagram. We do not start from any arbitrary form and try to basically optimize it. We start from a force distribution that we know that it's already optimized. We know that any structural form that you take from that would be in equilibrium to extract the form. So we can control the topology and also guarantee that the result would be compressionally or tensionally or the combined version of this. Anyways, this is something that I teach to graduate level students at Weitzman, and they make the physical model of that. And the moment that they basically make these spatial tensile models, they realize that the entire thing actually works and the principle holds. And through use of which they're able to explore a variety of different, spatially, I would say, different equilibriums that can be used as architectural spaces, architectural structures. Obviously, if you want to do this by hand, it's not feasible. It's going to take a long time. So we developed a tool. It's a computational tool for that. It's called Polyframe. It's a Rhino plugin. It's a free plugin for Rhino source software. And obviously there you can basically design the geometry of your force diagram and extract the topology and obviously the geometry of the form that would be in equilibrium according to the initial force distribution that you as a designer basically chose. So you can see that you can constrain your geometry and you can play with the geometric degrees of freedom, the edge length within the states of equilibrium without basically breaking that equilibrium between the form and the force diagram. Anyways, moving to the first built structure, this was a structure that we built as the first manifest of the method. This was built in a workshop that I taught for the first time after my PhD, right at the time that I started my career at Penn, at the Institute of Contemporary Architecture in Tehran. And the students basically really pushed it. I was afraid that this is going to work or not to begin with, but they really want to build a structure, and they finally did it. That's fantastic. So what you see in this structure is that this is a self-standing structural form. It's like a branching system, but it is quite unique in a way that the entire body, except the top chord, stays in pure compression, no bending moment, almost zero. And then the top chord is actually in pure tension. And the weight, or the self-weight of the top chord, basically keeps the rest of the member underneath in equilibrium. So what you see is actually 10.80 meters by 9.30 meter of a structure. In the widest span, it's actually 5.40 meters, and the height is 2.80. So because, again, we were using the geometry-based structural design methods, we were able to define the boundary condition in advance. And then we designed that as a compression-only spatial structure. So there are support locations at the top chord of the system and also support locations on the bottom. But we knew that we are not going to be able to support the structure on the top chord. So how can we keep the system in equilibrium? So if there is no horizontal force at the top chord, we know that we can actually manipulate the geometry of its force diagram. And the geometry of the force diagram is represented by rectangles here, right? So we can make the areas of the rectangle to become zero, which eventually make that rectangle to become a line. And as a result, it would change the force diagram to this configuration, and the top members would actually fall into tension. So as a result, we went ahead and we materialized it. But there was another point, because we knew that, first of all, there's not going to be any additional force on that. This is a self-supporting structure. We have to have applied load to keep the bottom part in equilibrium. And also we knew that the concrete is not going to take any tension force or any tensile force. So we wanted to make, first of all, the top chord out of concrete to use its self-weight, but we had to develop particular detailing for the top chord. So we came up with some plates that was basically precisely cut using water jet, and then inserted some parts that could precisely, again, transfer the tensile force between the top chord to make sure that the entire thing is in equilibrium. And then we can use its self-weight to keep the system in balance, right? So these are some of the images. So initially, this is in a historic site close to the palace of Shah, if you learn. So that was actually previous to the Islamic Republic. Anyways, it's a very important historic site. Initially they told us that this is going to be temporary, but they liked the piece, so now it's actually permanent. So it's fantastic. Anyways, to give you some ideas about the efficiency of the system. So the entire concrete that was used in the construction was 3.5 cubic meter of concrete, and it's been distributed in 50 cubic meter of a space. And it can take, the load bearing capacity is about 1,000 kilonewtons. So just imagine that we would like to design the same structure using conventional methods, right? Posts and beams with the same material, right? And the ultimum load bearing capacity that we can get from that is about 82 kilonewtons. As you see, there are beams, and they're basically, this frame is designed for bending moment, while the left one is actually designed for no bending moment. So if you want to make the existing system, the conventional one, to withstand 1,000 kilonewton, you have to increase the concrete used by 330%. And also the rebars should be increased by 10%. So you can immediately see why the system is more basically optimized in terms of the use of material, in terms of the carbon emission, et cetera, et cetera. So the next exercise that we had was to basically investigate the mechanical properties of such systems. So we were basically inspired by the very famous American Institute of Concrete test, which is a cylinder, and they would basically crash it to understand the compressive behavior of concrete. And obviously, if you use topology optimization, you would find the force flow, and you can find that force flow or the efficiency or the amount of material you can actually reduce from that. So we took the same geometry, the boundary geometry, and we applied the same method, and we designed a topology for that, geometrically. So there is a compression only structure for us. We fabricated in 2 different scales, but the size basically was 2 feet tall by 1 feet. So we did the load testing, and it was surprisingly high. So basically, the entire weight of the sample was about 25 pounds, which is around 12 kilograms, and it could take about 55,000 of loads, applied loads, right? The most interesting part of that was that the entire system exploded at once, which again proves the efficiency of the system, because if you size the members according to the areas of the faces, that means that you are going to have a constant stress field inside your structure. That also means that your structure should actually explode at the same time, right? Now, because remember, we're using geometry to design it, right? So there are so many different ways that you can subdivide these polyhedral cells to change the topology of the system without changing the boundary condition. In fact, in opposed to the common topology optimization that you can derive certain topology as a result, you can play with different topology here in our method. That as a result, you can basically have for the same boundary condition, you can have a variety of different topologies that they are compression only, but with different diameters of members and different valencies of the mass, right? So with this inspired us to take a look at the properties of these samples that can be generated using subdivision techniques of the force diagram. And what we realized is that subdivision at the boundary condition, together with the subdivision in the basically the members in the body of the system, can significantly improve the load bearing capacity up to even 3 times. Now, but the difficulty and the challenge was, okay, these are super intricate structures, and constructing these would be challenging because the spatial quality of that. Let's have those here. I'll get back to this problem with the current research in the end of my presentation. But obviously, we are in a design school. We have to basically showcase some of the work that we are doing in a design piece. You remember I talked about a convex cell can represent the equilibrium of a single node that is in compression. Well, the case is that not always the polyhedral system can be convex. In fact, you can have self-intersecting or non-convex force distributions, right? How do you describe systems that basically work with those? And how, more importantly, how you can control the polygons as a result of these self-intersecting polyhedrons, right? So for that reason, we developed a quadratic function that could describe the geometry of the polyhedral system using the edge length. And that allowed us to control the areas while constraining certain edge length. One really, really important aspect of that is that since the area represents the magnitude of the force, self-intersecting areas basically have 2 different regions that the sum of the basically areas in 2 regions with a signed sign basically represents the total magnitude of the force. It means that if you have a region that has a flipped normal direction and its area is equal to the another region, in total, it makes the area of your polygon 0. This is super exciting because now we can actually start with the compression only, and then we can force that force polyhedron to become actually 0 face members. Why this is useful? Because, for instance, you can have a structure that you can remove all the surrounding forces or horizontal system, horizontal applied loads, and basically design something that is, for instance, is basically utilized only for one direction of load and the reaction. So this was the structure that we designed according to that. So that all the horizontal forces are basically 0, and the top chord and the bottom chord will become tension to keep the body in compression. So this is if you're interested, the relative density of the structure is only 1%, and it can take up to 500 kilogram of load, right? So, but there is another invention here that because we were actually using the node-based assembly, obviously this makes the construction super hard because of the collision effect that you might have for the assembly. And so for that reason, to address that problem, we came up with a particular detail designing that could lock the members in a space as long as you have two members available. So this would actually make the assembly of the structure quite simple, right? So obviously we use some analog methods of construction and 3D printing for the formwork, but we 3D printed all the parts, demolded and assembled together to showcase the elegance and the efficiency of the structure. This was exhibited at the AAA Center in Philadelphia, and it was supported by Center for Art and Architecture, and received, by the way, the A Design Award last year. So I'm actually showing some of the built example, but the challenge was actually the top, the tabletop, which was meant to be built out of glass. So we realized that if you want to support the glass that spans 12 feet, we have to use a glass that has 2.5 centimeter thickness to be able to withstand its own self-weight, not even the applied loads. So this clearly shows that you have to design a system for bending moment, right? So in order to tackle this problem, we divided the top part into 3 segments, and also because of the construction constraints that we had, that work as a 3-hinged arc, right? So we could minimize the thickness of the top part to only 4 millimeter, and then we could actually get a structure that could basically span 12 feet. But the difficulty and challenge was that we had to basically form the structure into its particular geometry. So this is actually me holding glass after one test, which was relatively successful, but I'm not super happy with the quality of the glass. We improved that, and this is the final piece. Right. So currently we are actually taking this to the next level. We are looking into the 3D printing this out of concrete together with Sika and Pika's company here in the studio in the US. And this is another thing another venue that I would like to basically collaborate with you here at Perch and see how we can develop our own tools within the university to push this beyond the compression only and explore maybe compression and tension. Another ongoing project that I wanted to talk is related to an ultra-thin high-performance glass footbridge that we're working in a collaboration with Technical University of Darmstadt and Villanova University. So, as many of you might know, the design process, the form finding process, is not basically the entire design to construction step, right? Once you find the form, you still need to rationalize it for construction material. So I'm going to show you a simple example that is developed using graphical methods in 3 dimension based on reciprocal diagrams. And I'm going to show you how this simple example can immediately turn into something exciting by changing, just simply subdividing the force diagram as it's shown here, which is just a single tetrahedron, a single node in equilibrium. If you change the topology of the force diagram by subdividing it, suddenly the topology of the equilibrium structure will change, right? It would go from a single node to a shell. So this is very exciting. Yes, okay, we discussed this. Yes, you can control over the geometry of the force. You can control the force distribution. But more importantly, you get all the faces planar. That means that with the same technique, you were able to combine both form finding and fabrication. So you can have control over everything. So this actually inspired us to go for a structure made out of glass that is compression only, and also made of very, very thin pieces of glass that shows clearly the efficiency of the system. Also, we were actually aiming to eliminate any kind of additional detailing, like metal detailing that you usually see in glass structures at Apple Store, etc. We wanted to eliminate all those things and really concentrate on the glass property. Why? Obviously, yes, we were using because we can actually explore this equilibrium states and use the polyhedral geometry. But more importantly, we wanted to show that you can actually minimize the use of material. You can actually design glass structure that can be modular. So you can actually build blocks so you can assemble it together for a bigger structure. We can reinvent the structural detailing and put the emphasis more on the glass. And more importantly, if we can, if we can do this using the glass, right, which is one of the most difficult construction materials to work with, you can apply this to any sheet-based material and basically show the efficiency and efficacy of the method. So we did the preliminary study. Yes, the FE works well. Now we need to dive into the detail. The construction detail is actually where the devil's in, right? So we decided to make the structure out of a closed polyhedral cells, similar to the same technique. And these polyhedral cells should actually be made out of glass. So here we are using 5-axis water jet machine to cut the edges of the glass at a precise angle, so we can put together this glass cell, right? So right now, we performed the preliminary studies on the load testing of this glass cell. This is it's called hollow glass unit, or HGU. And it could take, you can see it yourself, the bottom red number is actually shows in kips, right? So 37 kips of load for a float glass, or basically window glass, right? Which does not have any additional layers of reinforcement. And also it is quite cheap, and it is held together with a tape. It is also quite inexpensive, and it's very much like a double-sided tape, right? But it works for glass construction. Anyways, the single unit actually showed a really promising result, and probably you saw this model at the innovation. If you pay attention to the second floor, this is actually the model made out of plexiglass sheets, to just as a demonstration piece. Hopefully, we will be able to complete the bridge by 2022, meant for Glasstec, Germany, Düsseldorf. But I will keep you posted. This is a work in progress. You remember I was talking about the buckling performance of funicular forms and basically the spatial forms. This is a new research by my PhD student, who is actually looking into the possibilities to take the cellular structure and translate it into two-manifold cellular systems. So using this technique, we are able to overcome the construction problems and generate a shell-based spatial system that can withstand the applied loads. Again, by the factor of 3, it can be improved, right? So this is also the basis of the research that we're also taking it to cellular materials, and we are pursuing that with McGill. And also, we were very lucky that was invited by, first of all, by Professor Xu Yang, and we received the National Science Foundation for the Future of Manufacturing grant, which is based on this method. I don't know how much time I have. I'm almost at the end of my presentation. I was just wondering, because I see you're basically on.
So we're at 2:11. So another 5 minutes, 5 to 10 minutes, and then we can save the rest for Q&A.
Sounds good. Sounds good. Okay. So I have another 5 minutes. So I'll actually show you another recent study. So far I was talking about, first of all, convex system. I was talking about self-intersecting. But it's also important that you know that for a single convex system, you are able to describe the equilibrium of compression and tension members, right? You can actually push one of the compression members to go to the other side and will become tension, right? So as a result, you can describe a variety of different geometries of the structural forms for the single force distribution. So the algebraic formulation of graphical methods, here we investigated in that, allowed us to have basically control over states of equilibrium for the same force distribution. For instance, this is an aggregation of convex polyhedral cells that in a common case represents a compression-only funicular synclastic structure. But then, because we can reparameterize the solution space, we can basically force certain members to go into tension. And as a result, we can have a compression tension combined system, which is anticlastic for the same, again, force distribution. And this is another configuration for the same force. So this is really exciting, because that allows us to explore a variety of structural forms right now that necessarily are not convex, right? with different. So the top one is actually the same Hooke's law that you see. If you flip a chain, you can actually get attention to compression. But the bottom ones are the new ones that were developed by us. So you can actually flip the form without flipping its force diagram, right? So why this is important? Because again, in the application in the cellular solids, we can basically use the system to develop a new types of auxetic materials, right, in three-dimensional space. Again, I'm not going to go into too much detail. Let's get back to nature to close it up. Probably for those of you who are working with natural structures, you know that nature has this tendency to distribute the force axially in its members, right? That's the way that nature actually reduces the use of material and achieves efficiency, right? In fact, Coleman, who was a developer of the graphic aesthetics at TU Zurich in 1866, was a close friend of Mayer, von Mayer, if you know him. And these guys basically inspired each other a lot. And von Mayer actually became the inspiration for Wolff's law later on, that he basically mentioned that if loading on a bone increases, the bone will become stronger to resist loading, right? So this actually has been taken to biology. And this also inspired us to look into the biological structures and try to find these traces of equilibrium forces, if you could describe it geometrically, right? As you see in many natural structures, you see the flow of forces in the form of pure tension or compression, right? So we took this idea and we investigated the possibly one of the most lightweight spatial structures, which is a dragonfly wing, right? So we analyzed that, the pattern of the dragonfly wing, and we realized that, and we took the force distribution geometrically from that, and we were able to reconstruct the dragonfly wing using the same method, and the force distribution and the thickness properly matches the same thickness that exists in nature. So this is super exciting because it tells us that the wing, for what load it has been designed, and it actually tells us how to reconstruct that for if we have the boundary condition load, now how we should basically go ahead and develop that internal structure. So I'll just show this to you. This is again another work of my PhD student, Hao, who's using machine learning to understand these patterns. But again, this is an ongoing research. And by the way, we are implementing this tool as an online web base supported by NSF. Soon it will be released. This is another work of my PhD student that you would be able to, on the web, on your browser, to basically play with these and understand the flow of forces for educational purposes, obviously. I'll just stop here if you have any questions. Sorry if I went really, really fast.
Yeah, thank you so much. That was amazing. So at this time, we're going to open the floor for questions. So please note the following. So we don't have a chat sort of window this time around. So if you have questions, please feel free to unmute yourself and go ahead and ask your questions. Okay, so let me, so I actually have a couple questions. So the structures are beautiful and fascinating. One question that I was wondering, and I'm not sure if you cover this, is, how do you decide, how do you build them? Like, what is the sequence in which you're supposed to put the different pieces together?
Great, so great points. This is actually, so one of the major, I would say one of the main limitations that the method has is that, or opportunities, I can say at the same time, it does not include material properties, right? So that means that this equilibrium states that you develop, assuming that your modulus of elasticity is really, really high, is scale independent. So you can basically build it out of any material. You can build it out of concrete or chocolate. You can expect that the behavior would be the same, right? Well, as long as you take care of that the deflection, because if the deflection is really, really high in your material, or your material is really, really ductile, then the system might not apply, because the system would not work as a compression only system, because the deformation of the geometry causes the system to go to experience bending moments. But as long as you make sure that you have certain level of stiffness in your geometry or the material that you're using, you can just go ahead and build it in different scales. Now, obviously, the reason that I actually showed you the range of material was to prove the fact that it doesn't matter what material you choose. You can basically apply it to glass. You can apply it to carbon fiber. I did not show actually an example of that, but there are an additional project. Concrete, masonry, steel, sheet-based material, and hopefully soon, together with Professor Xu Yang and his team and her team, sorry, we'll be able to show the application of this in multiple scales, right? But which is made out of synthetic material. So material decision and the construction for that, the construction type, is not decided in advance, but rather it actually goes hand in hand. One thing that I was hoping, and I should actually clarify here, that one of the reasons that I was basically interested in joining the Perch was that, frankly, I don't have any build space. And when I started at Penn, I did not have any equipment whatsoever. That's why this was good at the same time, but restricting a lot. Good because I had to search for any kind of collaboration that I can have with other universities, through which we learned a lot. But in the meantime, restricts us a lot. So now we are at the stage that after these couple of years, I was able to secure a little bit of funding to be able to establish a robotic lab. So we can basically look into the robotic manufacturing aspect of these techniques, because yes, we can design really efficient structures, but the fabrication is super challenging, right? Because this is three-dimensional system. We need to develop that. And that's by itself is a whole venue of research. And that is basically my next step. And I had this disclaimer at the beginning that I don't have much related to robotics to show, but that's exactly my intention. In fact, we are experiencing with 3D printing, but again, with the company, we don't have the facility at the school. But I'm hoping that with the new space, hopefully in the coming year, we would be able to invest in the robotic fabrication. And I'm really interested to work with the students and the faculty, obviously, to develop end effectors for particular fabrication process and manufacturing process.
Great, thank you. Are there any other questions? Yeah, I think it would be actually quite, oh wait, Andrew has a question. Andrew, go ahead and unmute yourself.
Hello, thank you for the talk.
Sure.
My question has to do with expansion. So do you have any idea or intuition how susceptible these structures are to stresses from thermal expansion? And do the joints that you use to assemble them, do those play any role in that? Like I'm thinking of concrete sidewalks, how the joint allows for expansion.
Yes,
Thank you.
So yeah, great question. Well, we didn't have that much time or experience in really investigating the effect of thermal expansion or contraction, right? But let me tell you, give you an example. The table example that I showed with the connection with the steel connection at both ends. We knew that concrete, after pouring into those parts, is going to contract itself, right? And this was really difficult to work with, because we knew that if concrete basically contracts, we won't be able to assemble the structure together. So what we did, we developed this detailing that had this anchor point, and the detailing was also anchored at the 3D printing formwork. So basically the 3D printing together with the steel bar could keep the concrete in its precise location. So we did not let the steel to move, but instead the concrete between that shrank, right? So as a result, we could still use that precise piece for the fabrication. We knew that the concrete had its own contraction, but it did not affect the entire process. But again, this is a very, I would say, this is a composite system, right? It's an interesting question to see how the contraction would directly affect the load bearing capacity. I don't know. Great direction of research in the future. Maybe.
Any other questions? Okay, thank you everyone for coming. And this is, again, stay tuned. There's gonna be another, so in addition to the graph on robotic seminars on Friday, we'll have more of these coming in the next couple of weeks, okay? Thanks again everyone for showing up.
Thank you very much. Thanks again for the invitation. Yes. Thank you.
Well, I think this is super interesting. I think from my perspective, I think a really interesting aspect of this is the sequence of assembly, yes. And how, because I suspect that you probably would end up with systems that are unstable if we do, sort of as you're assembling this sequentially, right? So the total system is guaranteed to have static stability.
Absolutely, absolutely. No, that's a really interesting area of research, that how you can actually come up with a system and an efficient method of assembly during the construction process, right? You know that if you reach to the end, everything is going to be efficient, everything. But yes, how you can keep the equilibrium or minimum equilibrium for the system during the assembly, because during the assembly you might experience bending moment, and that might be destructive because some of the members are not designed for bending moment, right? So yeah, I believe like robotic assembly, this would be the future, definitely. Either the robots themselves would take the parts along the members to assemble them, or certain robotic system that they can post tension the members in their location until the part is actually inserted. So there are definitely directions, but obviously it has to be looked properly with respect to the scale, right? Because the scale is really.
Well, the other thing I was thinking. Yeah, so the other thing I was thinking about also was the fact, in your software, right? Because since you can break these things down into subcomponents, potentially there's an interesting search problem, because you can, I would say if you had two candidate realizations, right, you could potentially think about, which one may be easier or harder to assemble because of the sort of degree of instability based on this assembly sequence. And then again, thinking about sort of the can you somehow use the ability to decompose into substructures in order to think about assembly sequences. So I thought that was some of the things that, and this seems to match really nice, match nicely because of their kind of search type problems, right?
Exactly.
And so yeah. No, so in a way it sort of recalls a lot on these sort of planning algorithms that we often think about. Yeah.
And the kinematic degrees of indeterminacy of the system, as you said. So how we can actually come up with a system that might actually be kinematically determinate during the assembly. So you prevent from that.
That's right.
This is really
Yeah, that's an interesting. Anyway, I just thought this was great because at some point, I think it was when I was an assistant professor, I was thinking about sort of assembly with these little robot arms, and this was some of the Da Vinci self-supporting bridge, right? It's sort of one of these examples where you have this, you can almost do the construction algorithmically, in the sense that it's sort of a sequential set, like once you assemble certain modules, you can get the other modules.
The reciprocal pieces that you're referring to, yes, they can rest on top of each other while you actually do that.
That's right. And so one of these things when we're thinking about the planning problem was exactly sort of how would you sequence it and how would you design sort of the assembly strategy, right? Yep. If you can work with these types of structures that are more regular or sort of self-repeating in a sense, and so I thought this is really cool. This is super. Yeah. But thank you so much. This is a great talk, and just so you know, the talk is recorded, and so this way for the faculty members who can't who were not able to be here in person, they'll be able to look it over. And then we'll be in touch soon. So thank you so much.
I really appreciate it. Thanks for the invite again. Thank you.
Yeah, thanks. Bye.
Bye-bye.